Good day, Sir Arman. Good day, everyone. I would like to introduce myself first. My name is John Rainer Diaz from BSIT2, and the topic I chose is first come, first served, and shortest job per CPU scheduling. Why did I choose this topic? Because it is a simple and easy to understand. First come, first served provides fairness by treating all processes equally, giving them an equal opportunity to run. First come first served guarantees that every process will eventually get a chance to execute as long as the system has enough resources to handle all the processes. While shortest job first is probably optimal in that for a given set of processes and their CPU burst execution times, it gives the least average waiting time for each processes. But there are similarities between these two CPU scheduling algorithms. The first come first served scheduling algorithm, the shortest job first scheduling algorithm are two different approaches to process scheduling in an operating system. While they have distinct characteristics, there are some similarities between the two algorithms. First come first served and non-preemptive shortest job first share some characteristics such as their non-preemptive nature, simplicity, and deterministic behavior. However, their fundamental scheduling criteria are different, with first-come first-served prioritizing the order of arrival and non-preemptive shortest prioritizing the shortest first time. Let's go with the first-come first-served scheduling. What is first-come first-served scheduling? Is a simple and straightforward scheduling algorithm used in computer operating systems and various other applications to allocate resources to tasks or processes in first come first served scheduling. Tasks or processes are executed in the order they arrive in the queue. The first task to arrive is the first one to be executed, and subsequent tasks are executed in the order in which they arrive. In the first come first served scheduling algorithm, as the name suggests, the process which arrives first gets executed first. Or we can say that the process which requests the CPU first gets the CPU allocated first. First come first serve is just like the FIFO. FIFO, known as first in first out queue data structure, where the data element which is added to the queue first is the one who leaves the queue first. This is used in batch systems, and it's easy to understand and implement programmatically using a data structures where a new process enters through the tail of the queue and scheduler selects process from the head of the queue. The main advantage of first come first served scheduling is its simplicity, as it's easy to implement. However, it has some significant drawbacks, such as the potential for a phenomenon known as convoy effect. In the convoy effect, a long-running process can block other shorter processes behind it, causing longer waiting time for those processes. First come first served also doesn't consider the priority of processes of their execution times, which can lead to inefficient use of resources in a certain situation. While while first come first served is not suitable for all scenarios, it can be used effectively in situations where simplicity and fairness are more important than optimizing resource utilization and response time. In practice, more complex scheduling algorithms such as round-robin, priority scheduling, or shortest job first are often used in operating systems to better meet the requirements of different types of workloads and applications. Average waiting time is the average waiting times of the process in the queue, waiting for the scheduler to pick them for execution. The lower the lower the average waiting time, the better the scheduling algorithm. So let's consider this the process P1, P2, P3, and P4, given in the below table, arrives for execution time in the same order with the arrival time 0, and given burst time. Let's find the average waiting time using the first come first served scheduling algorithm. As we can see, waiting time for P1 will be 0. P1 requires 21 milliseconds for completion, hence waiting time for P2 will be 21 milliseconds. Similarly, waiting for the process P3 will be execution of P1 plus execution time for P2, which will be 21 plus 3 is 21 plus 3 milliseconds is equal to 24 milliseconds. For process P4, it will be the sum of execution times of P1, P2, and P3. So 21 plus 23 plus 26 plus 2 is equals to 32. And this and the average waiting time will be 0 plus 21 plus 24 plus 30 divided by 4 is equals to 18.75 milliseconds. So let's go to shortest job first. What is shortest job first? Shortest job first is a scheduling algorithm used in operating systems to allocate CPU time to process is only known as shortest job next and is based on the principle of selecting the process with the shortest burst time to execute first. The idea behind SJF scheduling is to minimize the average waiting time for processes, which helps in improving the system efficiency. Here's how the SJF scheduling algorithm works. When a new process enters the ready queue, the scheduler examines the burst time execution time of all the processes currently in the queue. The scheduler selects the process with the shortest burst time among the available processes. This is the process that will be scheduled to run next. If multiple processes have the same shortest burst time, the scheduler can use different tie-breaking methods such as first come first served or priority scheduling to decide which process to run first. The selected process runs until it completes or preempted by a higher priority process or an interrupt. After the execution of a process is completed, the scheduler repeats the process selection based on the remaining burst time of the processes in the ready queue. Shortest job for scheduling can be either preemptive or non-preemptive. Preemptive shortest jobbers in this version, a running process can be interrupted and replaced by a shortest job if a shorter job enters the ready queue. This approach is more complex to implement but can lead to better response times. Non-preemptive shortest jobbers in this version, once a process starts executing, it continues until it finishes, even if a shorter job becomes available. This is simpler to implement but may lead to longer response times for some processes. One of the main challenges with the shortest job versus scheduling is the difficulty of accurately predicting the exact burst times of processes in a real-world scenario. Estimating burst times can be inaccurate, leading to suboptimal performance. To mitigate the issue, some variations and heuristics, like the shortest remaining time first algorithm, are used in dynamically adjust scheduling decision based on the remaining time of process. Advantage of shortest job first is minimizing waiting time. SJF scheduling minimizes the average waiting time for processes by executing shortest job first. It reduces the time processes spend waiting in the ready queue, leading to quicker turnaround times, efficient utilization of CPU. Shortest job first scheduling maximizes CPU utilization by giving priority to processes with shorter burst time. This helps in making the most efficient use of the CPU as it focuses on executing processes quickly. As you can see the chart above processes, P4 will be picked up the first. It has the shortest burst time, then P2 followed by P3 and at last P1. We schedule the setup process using the first come first serve algorithm in the previous topic and get average waiting time to be that 18 milliseconds, whereas shortest jobbers, the average waiting time comes out for 4.5 milliseconds because 0 plus 2 plus 5 plus 11 divided by 4 is equals to 4.5 milliseconds. In shortest job versus scheduling, the shortest process is executed first. And that's all. Thank you.